So today's technical presentation will be about communication protocols and embedded systems. Communication protocols are important in computing because if you ever want to read data from a sensor, that sensor needs to send data somehow, and that's typically through a communication protocol. So we'll go over four very common communication protocols: I2C, SPI, UART, and CAN bus. So we'll start with I2C. I2C is half duplex, meaning that only one device can send data at a time. It was developed by Felix Semiconductors, now known as NXP. And then usually it's an interboard communication protocol, meaning that two ICs will send data between each other. Um, and then it's composed of two lines, SCL and SDA, serial clock and serial data. So when a device wants to start communication, it will pull the SDA line low while the SCL while the clock line remains high, and then we'll send an address. Typically, it's 7 bits, but it can be 10 bits so you can fit more devices on a single bus. Then that's followed by the read or write bit. In this particular instance, it's going to be a write, and then you have your ACK, your acknowledgement bit, and then you have your data, which is sent byte by byte. And then after every byte, you always have your acknowledgement bit. And then multiple bytes can be sent through like a byte. You have your ACK, byte, ACK, byte, ACK, and that can continue on for however much data the master or the slave needs. And then after the final byte has been sent, a stop condition will occur, which is when the SDA line transitions from low to high while the clock line is high. Next comment is going to be SPI, Serial Peripheral Interface. This communication protocol was developed by Motorola. Very short distances. Again, it's interboard, much like I2C. It is, however, one of the fastest communication protocols, though. It's full duplex, meaning that both the master and the slave can send data at the same time. And then it's four lines. Your serial clock, MOSI, which is master out, slave in, your MISO, master in, slave out, and then your chip select. So how this will generally work is that the master will pull this chip select line low for the slave that it wants to communicate with, and then it can send uh, any data that it needs to the slave, and then the slave can also send data to the master through its MISO line. SPI doesn't really have a defined communication or a defined frame per se. It can kind of send bytes to the slave, and then the slave can respond how it's programmed to the certain bytes, and they can send data back. It's not it's pretty implementation specific, but this is the general um, protocol that you might see on like a logic analyzer. And then we have UART, Universal Asynchronous Transmitter, Asynchronous Receiver Transmitter. So it's two lines, receive and RxTX, and then it's full duplex, meaning that both the device and the master can send data at the same time. And unlike the last two protocols, this is asynchronous, meaning that it's assumed that both the two devices that are communicating with each other have the same clock rate. So this right here is a typical UART frame. You have your start, which is when the line is pulled low, and then you send your data bits. Your high, you pull the line high, or yeah, pull the line high for a 1, and then pull the line down for a 0. And then you have your optional parity bit, and then you have your stop condition, which is just when the line is released. There's no really defined voltages um, that like a 1 or 0 is considered. It's pretty implementation specific. And then lastly, you have your CAN bus, controller area network. If you're a car guy, CAN bus is used in cars, and for a good reason. It's probably one of the most reliable communication protocols out of the four that I mentioned. It is asynchronous like UART, and it's half duplex. And unlike the other communication protocols, it uses a differential signal. The reason why this is so reliable, if you can see in this image, you can see that there's a bit of noise here. And you see that despite that, the data can still be read fine. And the reason why is because it reads the difference between the two signals instead of like a single, like relative to 0 volts or something like that. Because of that, because also since noise tends to affect both the CAN high and the CAN low lines at the same time, um, since CAN measures the difference between the two lines, and the difference relatively remains the same even when noise is present. data can propagate still pretty well under noise, and it's one of the reasons why it's so effective or so reliable. So this is the general frame. It gets pretty detailed, but you have your starter frame, your arbitration, which is basically your ID. You have your control, your data, and by the way, the control is where you'll probably send how many bytes you want to send. You have your actual data. You have your CRC, which is called a cyclic redundancy check. It's one of the ways that can ensures that the data went that got transmitted is actually correct and not actually affected by noise. And then you have your end of frame. You'll see here that there's some stuff bits. Essentially, what that means is that after five of the same bits, like for example, 5 ones or 5 zeros in a row, it puts a stuff bit in there of opposite polarity, just so that the CAN bus doesn't register an error. But yeah, these are the four common communication protocols that you'll see in embedded systems, and it's probably going to pop up on pretty much a lot of interviews, a lot of embedded interviews rather. So these are definitely really important to know.